Hi, I'm Wei-Nai Chen from the Academia Sinica, Taiwan. I'm going to introduce how do we use LiDAR to monitor the environment in Taiwan. So, what LiDAR can do for the environmental monitoring? At first, certainly that will be the concentration of air pollutants based on the misscheduling of aerosols, and the microphysics of aerosol, including aerosol types and the hygroscopicities. But I will not cover this part today. The next thing is the boundary layer methodology, including the diurnal variation and the local scalation, because it will directly affect the spatial distribution of the aerosols and the other pollutants. The last thing is the source approach. The purpose is to locate the pollutant sources. Today's contents are based on our results of aerosol LiDAR and Doppler wind LiDAR measured in Taipei and Taichung. At first, I will make a quick introduction of LiDAR, but I will skip how to calculate and how to interpret the optical characteristics of the aerosols that can be derived from LiDAR measurements. For the concept about the Doppler wind LiDAR, please see Dr. Dai's talk in the later session. Then I will demonstrate a case of local transportation, and then is the mixing layer measured by the aerosol LiDAR and Doppler wind LiDAR, including the impact of complex carriers on planetary boundary layer. And the last is the source approach. This slide shows the system configuration of our two wavelengths and the Raman depolarization LiDAR and the coherent Doppler scanning wind LiDAR. In the first, I want to emphasize why we not only measure the aerosol in planetary boundary layer, but also the wind. In general, the structure of planetary boundary layer is determined by convection and wind structures. The concentration of pollutants then is determined by the direct emission, horizontal transportation, vertical mixing, and the height of the mixing layer. So, we need to know the wind structure to study where the aerosol comes from. As a sample, this slide shows aerosols was accumulated and trapped inside the mixing layer and then degrade the air quality. Before presenting our, I would like to make a very short introduction about the LiDAR equation. The LiDAR equation shown here is used to describe the amplitude of a received signal, which is inversely proportional to the square of the distance, and positively proportional to total backscatter coefficient, including aerosols and molecules, and the round-trip transmission. If we multiply the amplitude of the received signal with the square of the range, that becomes the simplest LiDAR parameters, which can refer to the concentration of the aerosol. We usually call it the range-squared signal, or attenuated backscatter. This will be the LiDAR parameters we use to present our results. Certainly, the extinction or backscatter coefficient can be calculated on LiDAR measurements, but I will not cover this part today. So, if we have vertical profiles of range corrected signal, backscatter extinction coefficient, and wind direction and wind speed, how can these measurements apply to environmental research? At first, let me demonstrate a case of a translocal transportation. In the LiDAR profiles, you can see the aerosol concentration suddenly increase around the noon time. And from the video, you will see the pollutant suddenly appear at the same time. From the satellite image, it shows aerosols were on the ocean in the morning and then transported to inland around the noontime. However, those satellites can show the horizontal distribution of the plume. We still need LiDAR to reveal the vertical distribution of the plume. In the next part, I will introduce the results about the planetary boundary layer measured by ME LiDAR and the wind LiDAR. This slide shows the vertical profiles measured by radio sound, aerosol LiDAR, and wind LiDAR. In the figure, you can notice aerosol was nearly well missed below the missing layer. Above the missing layer, you can see the wind direction changed from the west to east, and then the wind direction again changed above the planetary boundary layer. Aerosol concentrations are also suddenly decreased in the planetary boundary layer. We believe this is an indication of local circulation of sea breeze, sea land breeze, and the mountain valley breeze. This slide shows the height of the missing layer averaged from 1 year LiDAR measurements in Taichung. In general, missing layer height is higher in summer and lower in the winter, as expected. In general, the missing height should be negatively proportional to the concentration of pollutants, and then positively proportional to surface temperatures. However, when we calculated the correlation between the missing height and the surface temperature and the wind speed, it can be noticed that the correlation usually are very poor. That means the height of a missing layer is dominated by other reasons. And we also noticed we cannot see any correlation between missing height and the surface temperature and the wind speed. In this slide, demonstrate when Taiwan is under winter monsoon, the dry airs were from northeast. The temperature is lower in the night, but you can see the missing height is keeping high. So there is no correlation between the missing height and the surface temperature. Same thing also happened when Taiwan is under summer monsoon. In this figure, you can see the moisture area were from southwest with cloud layer at about 1 kilometer. Then again, you can see the diurnal variation of missing height are totally different from surface temperature and the wind speed. In previous figure, you might notice the missing height in the March much higher than missing height in the other seasons. Since we know only when Taiwan is under weak synchronic condition, the missing height will have clear diurnal variation. So we will try to average the missing height only for the case in the weak synchronic condition. The result is shown here. In this figure, you can see the diurnal variation of a missing height in all months are very similar. The missing height, thin blue line, is around 300 meters to 500 meters in the night and about 1 kilometer in the noontime. So, and the interesting thing is the missing height is not significant higher in the summer. So we are still investigate the possible reason, but we are thinking that might be related to local circulation. When Taiwan is under weak synchronic condition, we noticed the wind direction in the lower boundary layer is usually opposite from the wind direction in the upper boundary layer. In this figure, the red arrow represents winds from the west. The black arrow represents winds from the east. You can notice the changing of the wind direction. For example, in the night, you can see the wind direction is from the east at a height below 500 meters. But at the height above 500 meters, the winds are from the west. In the noontime, the wind direction changes from east to west. And again, you can see in the upper boundary layer, the wind direction is opposite from the wind direction in the lower boundary layer. Then, in the nighttime, again, you can see the wind direction changes from the west to the east. And again, you can notice the wind direction is opposite in the boundary layer, upper boundary layer. We believe this phenomenon is caused by the local circulation because Taiwan is surrounded by ocean and there is a central mountain with a height of about 3,000 meters. So when the air comes from the ocean to the inland, air will be stopped by the mountain and then elevated to the upper boundary layer and then back to the ocean. So if we look at the local circulation scheme proposed by the Crossman, that is very similar to our results shown in previous figures. To further investigate the flow pattern of local circulation, we try to equip aerosol LiDAR and wind LiDAR on a van or pickup truck to measure the cross-section of planetary boundary layer in the western plain of Taiwan. This slide shows our vehicle-based Doppler LiDAR and aerosol LiDAR. This mobile aerosol LiDAR is part of Dr. Roger Raman's work when he was in Taiwan. A cross-section of the planetary boundary layer measured by the mobile aerosol LiDAR is demonstrated here. So you can notice the spectral distribution of the planetary boundary layer is ununiform in the western plain. This figure demonstrates the flow pattern of local circulation measured by wind LiDAR and the mobile aerosol LiDAR. The wind LiDAR was fixed at the coastal region, and the mobile aerosol LiDAR measures the cross-section of a planetary boundary layer from the west to the east. From the result of the wind LiDAR, the wind direction in the upper and the lower boundary layer again are opposite. And at the height of the return flow from the mountain, an aerosol or cloud layer can be observed by the mobile aerosol LiDAR. The mobile-based LiDAR can not only use to review the flow pattern of local circulation. During the experiments, we also noticed the complex terrain will cause significant impact on the structure of a planetary boundary layer. This figure shows the cross-section of planetary boundary layer measured by mobile aerosol and wind LiDAR. In the figure, the black curve is the elevation of terrain. So you can see there is a small hill at the coastal region. It can be noticed the height of the mixing layer is shallow in the coastal region. After crossing the hill, the height of mixing layer elevated from 500 meters to 1.2 kilometers in the inner area. This slide shows more observations to review the impact of a complex terrain on the planetary boundary layer. In the left figure, again mixing layer elevated in the inland after cross the hill. In the right figure, thick cloud layer formed in the west side of the hill. And in the east side of the hill, the weather is clear and the aerosols were elevated to higher than 1 kilometer. To confirm the complex terrain will have significant effect on the structure of the boundary layer, we upgrade the mobile aerosol and wind LiDAR on a flat plane at the Jiayi Yunlin area. In the figures, you can see the height of the mixing layer is nearly uniform from the coastal area to the mountain. So these results indicate the complex terrain will have a significant effect on the evolution of the planetary boundary layer. In the last part, we will demonstrate how we try to approach the source of pollutants by LiDAR. This experiment was made in Taichung City because there is a power plant and it is the largest CO2 emitter in the world. This figure shows the windrows and the probability distribution of pollutant episodes based on the wind LiDAR measurements. From the windrows, it shows the wind mostly are from the north or from the south. But from the probability distribution of polluted episodes, you can notice the pollutants mostly are from the west direction, and the power plant is located in the west. In order to understand the impact of power plant on the regional air quality, we designed an experiment to install a scanning wind LiDAR in the power plant to directly measure the spatial distribution of the plume from the power plant. The location of the wind LiDAR is just right here. This slide shows the results of a scanning LiDAR. In the right figure, LiDAR horizontally scanned the aerosol distribution. In the figure, we surprisingly noticed there is some huge aerosol plumes located in the north direction. And this direction, this plumes is not belong to the power plant because there is an industrial park located there. In the left figure, LiDAR vertically scanned the north direction. And in this figure, you can see the plume from the power plant can be observed. But at the area of the industrial area, there is some very huge aerosol emission over this location. So that indicates the emission sources for the power plant is maybe not the only major reason for the better air quality in the Taichung City. Other sources, for example, this industrial park is another important emission sources which will degrade the air quality in the Taichung City. One more thing we found that is the LiDAR measurement might be helpful to improve the regional air quality. In the left figure, the vertical wind profiles indicate strong wind was located at a height below 400 meters. Aerosol will be easier to dissipate in this region. At a height between 500 and 800 meters, the wind speed is low, so the aerosol will be tended to accumulate in this region. But when we look at the distribution of the plume from the chimney of the power plant, the result shows the plume will directly go up to 900 meters with the upward speed about 10 meters per second, and then accumulated at a height between 600 meters and 1,000 meters. So that means the effect changing height is too high. So the plume will accumulate at the region around the power plant. If the effect changing height can be reduced to 400 meters, the plume will be quickly dissipated to the other region. For example, the ocean or the inland. Then the regional air quality will be improved. Basing on the aerosol and the wind LiDAR measurements, we can easily find the vertical distribution of the plume in the source area is related to the vertical distribution of the wind. In the figure, you can see the aerosols were accumulated in the weak wind speed regions. So our results indicate aerosol and the wind LiDAR measure can precisely locate the emission sources and also can provide solutions to improve the regional air quality. The air quality is a big issue in Taiwan. We are now trying to apply model simulation, such as large eddy simulation, to simulate the spatial distribution of the plume from the major emission sources. This slide shows two cases simulated by the large eddy simulation. This model is developed by the University of Hanover, Germany, and this will be at the end of my talk. So in the figures, you can see the plume emitted from the chimney. It will transport to the south and then flow back to the north. So this is another simulation which shows the plume directly goes from the coastal area to the inner land. To the end, we presented the spatial distribution and the time height distribution of the aerosol and the wind measured by our aerosol LiDAR and wind LiDAR. The most important information is the LiDAR can not only used to monitor the environment, but also be helpful to provide a solution for the regional air qualities. Thank you for your listening.